Welcome back. In this section, we will go from situations where you could treat an object as a particle, meaning that the size of the object didn't matter, to situations where we treat an object as a rigid body, where the size does matter. And for that, the concept of forces is not enough to analyze these kind of situations. We will also need to add the concept of moments. Imagine that you have a railway crossing gate. This point here, it's the center of mass, or cm, of the gate. The mass of the gate is 100 kilograms. In general, if you have a body like this rod, and we don't have to assume constant mass density, let's say that you have more mass concentration on the left and less of it on the right, then there is a point which is called the center of mass, or cm, and all it means is that if I apply a force F1 down on this rod exactly to this point of cm, then this rod will only accelerate down. A would be acceleration. But this force will not cause the rod to rotate. However, if I take this F1 force and I apply it, let's say here, then that will still cause the rod to accelerate downwards. You would still have here the acceleration A, but in addition to that, this force F1 will also cause the rod to rotate clockwise about this point of center of mass. And the same thing applies to 2- and 3-dimensional objects. You have a random mass distribution in those objects, and somewhere there is a point on this 2D object and inside this 3D object that are their center of masses. And if you apply a force to these objects precisely to where you have those center of masses, then these objects would start to accelerate in the direction of those forces, but they will not start rotating. So that's the case when they are on their own. But in our crossing gate example, the gate is attached to a pin at point A. And of course, it also rotates about that point A. That's how the mechanism was built. Then in addition, you have this counterweight here that also rotates about point A. The mass of this counterweight is 250 kilograms. And this would be the center of mass of the counterweight. Let's call the center of mass of the gate GR and the center of mass of the counterweight GW. And again, the system is built in such a way that both the gate and the counterweight rotate about point A. But the reason why I specify the center of masses of these two objects is because since they have masses, that means that they also experience the force of gravity. Now, the force of gravity is a distributed force. It means that if we, for example, take this rod, then every single molecule in this rod experiences force of gravity. So let's say that this molecule is Ma, this one is Mb, then this one is Mc, and this one is Md, and that means that here you would have Ma times G, then here you would have Mb times G, Mc times G, and Md times G. So G is the gravitational acceleration. Remember, it's 9.81 meters per second squared. So the force of gravity of each molecule is the mass of the molecule times G. And of course, all these molecules, they have different locations in the rod. And if you add up all the forces of gravity of all the molecules in the rod, you will get the total force of gravity of the rod. But in order to make our analysis simpler, we can simply take our total force of gravity and we can apply this force of gravity like this to a special point called CG, which stands for center of gravity. And the thing is that in most cases, center of gravity can be assumed to be the same like the center of mass. So CG equals CM. And of course, this FG total, it would be G times, and then you have MA plus MB plus MC plus MD and plus all the other masses of all the other molecules inside the rod. This representation here on the right is not the reality, but it's an equivalent representation of the reality for as long as we assume that this rod is rigid, meaning that we assume that it cannot bend. If we assume that, which is a reasonable assumption, when indeed the rod bends very little, then that means that using both representations, your object, your rod, will behave exactly in the same way. It's a common practice in engineering. You have the reality on the left, but in order to make mathematics easier, you find an equivalent representation of the reality which is easier to work with, and that equivalent representation needs to make the rod behave exactly in the same way like it would in reality for as long as you assume that the rod cannot bend, which again is a reasonable assumption if it indeed almost doesn't bend. Since Fg total is applied to the center of gravity or to the center of mass, the object will accelerate down in the same direction of Fg total, but this force of gravity will not cause the rod to rotate because it's naturally applied to the center of mass. Note that this is not 100% true. It's a simplification. As it was said before, in reality, the force of gravity goes through Cg and not through Cm. And in reality, Cg and Cm are different concepts. In reality, they are not the same. And that difference would actually make the rod rotate about Cm, which makes sense because if this is your Cg, center of gravity, then this is your force of gravity, but then your Cm is actually this point here, so there is a difference between them, and that would cause the rod to rotate about the point of Cm, the center of mass. However, in most of the everyday applications, the difference between them is so tiny that you can simply say that Cg is more or less equal to Cm. In most everyday applications, you can easily make this assumption. Their difference is negligible. If you're a space engineer, then you have to take that difference into account, but not in regular statics problems. Nevertheless, I'll cover that more in the section for distributed loads. Over there you will see the difference between the center of gravity, center of mass, and something called the centroid. And so that's why I tell you where the CMs of the crossing gate and the counterweight are. If you know their total masses, which you do, the gate is 100 kilograms and the counterweight is 250 kilograms, then you can calculate their total forces of gravity, which would be 100 g newtons in this case, and 250 g newtons in this case, and then these two force vectors, they would go through their respective center of masses. That's why I specify these 2 points here, the center of mass for the gate and for the counterweight. Now we have talked about the rigid body assumption. Like I said before, it means that the object cannot bend, it cannot deform, it's completely rigid. And again, as mentioned before, it's a reasonable assumption if the actual deformation is very, very small. For example, if you have a beam here and you stand on top of this beam, then in reality, this beam deforms a bit. However, it's so small that for statics problems, you can simply neglect it. You simply assume that the beam doesn't deform at all. That's called a rigid body assumption. And now, if you look at our crossing gate and counterweight example, then you can clearly see that unlike in the previous sections, where the size of the objects did not matter, now it does matter. Both the crossing gate and the counterweight rotate around point A. That's the pin they are both connected to. The perpendicular distance between FGR and point A is 2.75 meters, and between FGW and point A, 0.25 meters. And so the fact that there are perpendicular distances between point A and the gravity forces, that makes the entire structure want to rotate either clockwise or counterclockwise. And now this tendency of rotation, what does it depend on? Well, it obviously depends on the forces, right? It depends on FGR and FGW, but not only. It also depends on the perpendicular distances between the forces and point A. For example, this point here, that's your GR, and this point here, that's your A. This is this case here. The total length between these 2 points is L1. The perpendicular distance between point A and the force of gravity, FGR, that's 2.75 meters. And so obviously, this perpendicular distance creates tendency to rotate about point A counterclockwise. But what if you had a greater perpendicular distance between GR and point A? So the total distance is L2, for example. You have the same force here, FGR, and now the perpendicular distance between FGR and A is 4 meters. You can intuitively feel that it will create a stronger tendency to rotate counterclockwise about point A. You can feel it when you hold the bag in your hands. So this is your bag, and here's the force of gravity of that bag. The bag is the same, its force of gravity is the same, but the further your hands and the bag are from your body, the harder it is to hold it. Why is it like that if the box has the same mass and therefore the same force of gravity? That's because in addition to downward acceleration, which is the same for both cases, your muscles are also fighting the tendency of rotation, which in the second case, on the right, is bigger, because your bag is further away from your body. So your muscles are also fighting against rotation about this point. Let's call it point B. And here as well. This is your point B. And it's harder to fight against this rotation in the second case on the right. And so this tendency of rotation can be quantified. And we do it with moments. This is the definition. M, which is moment, equals F times D. F is force, and then D, that's the perpendicular distance, or in other words, the moment arm between the force and the point you're measuring your moment about. In our crossing gate example, we measure the moment about point A. Also, according to the convention in 2D, in 2 dimensions, a counterclockwise moment is positive and clockwise moment is negative. Finally, note that I stress a lot perpendicular distance between the line of action of your force and the point you're measuring your moment about. Note that the real distance between FGR and point A is larger. In this case it's L1 and in this case it's L2. However, we should not consider that length to calculate the moment about point A. And that's because it has a component that is parallel to the force FGR. Let's call this one L1 parallel and this one L2 parallel. If I get rid of these perpendicular distances, then I will have this situation. This is my point A, this is GR, this is L1 parallel, and this is FGR, and then here you have point A, this is L2 parallel, and this is FGR. You can see that in both cases, rotation cannot happen. The parallel components do not contribute to rotation. You need perpendicular distance for that. Therefore, in the moment equation, M equals F times D, this D is the perpendicular distance between this force and point A. Here it's 2.75 meters and here it's 4 meters. Because it's the only one that matters in creating rotation about point A. And now I have an exercise for you. You know the mass of the crossing gate and the mass of the counterweight, and you know their perpendicular distances to point A. So what is the net moment that comes from the crossing gate and the counterweight? You can get the net moment by adding up the moment from the gate and from the counterweight. Try it out by yourself first and then see the solution in the next video. Thank you very much. Welcome back. So let's now find this net moment. So again, this point here, that's A. Then here you have GR, and FGR equals 100 G newtons. Then this point here, that's GW, and here you have its force of gravity. FGW equals 250 G newtons. This perpendicular distance is 2.75 meters, and this one here is 0.25 meters. Let's first calculate the moment from the crossing gate. As mentioned before, the typical convention is that a counterclockwise moment is positive, and so the moment about point A due to this crossing gate is the following: 100 G times 2.75. This one here, that's the force, and this is the moment arm. The force is in newtons and the moment arm is in meters. And so that equals 2697.75 Newton meters. So that's the unit of a moment. It makes sense because you have newtons here and meters here. And now the moment about point A, due to the counterweight, that would be minus 250 g times 0.25. That will give you minus 613.125 Newton meters. The reason why you have this minus sign here is because the moment due to the counterweight about point A will give you a clockwise moment, which according to our convention is negative. So this one, what I put here, this is just by default. So by default, a moment is positive when it's counterclockwise. But if in reality your moment is clockwise, then it's negative. And of course, in the first case, you have a positive moment because due to the crossing gate, it's counterclockwise. And now, the net moment about point A equals the first moment that you have here plus the second moment, which is this one here. So this is the first moment, it's positive because it's counterclockwise, minus the second moment, which is negative because it's clockwise. That will give you 2084.625 Newton meters, or approximately 2.084 kilonewton meters. It's better to express it in kilonewton meters here. And there you go. This is your net moment about point A. It's positive, which means that the tendency to rotate about point A is counterclockwise. If you want it to be clockwise, then you either increase the counterweight mass or you place it further right from point A, or you do both in order to increase the net moment in the clockwise direction.